So I am starting the session now. Yeah, very good evening. So there is some network issue in my area, due to which the session may be a little bit fast, right? Right, I am starting now. So hi everyone, I am Anuj Kumar, and I am the PMR of TA for this course. This is assignment 5. Okay, so we will discussing the bonding in the complexes related questions. Okay, so this is the assignment one, the questions for the assignment five. The question one says which condition is required for a spontaneous reaction if temperature and enthalpy change remains constant. Okay, the formula is delta G equal to delta H minus T delta S, right? So these two terms are constant, temperature and enthalpy, right? So for spontaneity, what will be the required condition? Using simply mathematical calculation, you can directly uh, get an idea if this value is increasing, right? Delta S value is increasing, so overall terms, this term will be more negative. Okay, so that's why the delta G value will be more negative, right? Okay, I will explain in the next slide. Moving forward to the next one, what do you mean by chelation? Okay, I think you already know that. Okay, so there are four options. It is a type of bonding of ions and molecules of gelating ligands to the metal ions. Multiple number of metal ions are bound within the monodentate ligand pocket. Yeah, in this process, a complexing agent is used for metal binding, or chelation is used to insert heavy metals into the blood. Right? Basically, chelation is not used for inserting. It is basically used to extract heavy metals, right? Because metal can easily form the coordinate bond with the ligands, right? So here is the explanation. Delta G value will be negative for a spontaneous reaction. According to thermodynamics, delta G equal to delta H minus T delta S, right? So if temperature and enthalpy change is constant, the entropy change will be positive for a spontaneous reaction. So the delta G will be more negative, right? And chelation is a type of bonding of ions and molecules of chelating ligand to the metal ions. Okay, it involves the formation or presence of two or more separate coordinate bonds between a polydentate, which is basically multiple bonded ligand, and a single central metal atom. Okay, so chelation is the process of administering a medication to remove heavy metals from the blood, not for inserting. So Uh, this one is the right answer for the second one, and this is for the first one, right? So moving to the next two, what type of ligand? EDTA, ethylene diamine tetraacetate. Basically, this one, CS2, CS2, and COO negative, COO negative, and similarly here. Okay, so just count the atom which can donate the electron pairs to the central metal atom, and you will get the answer. Okay, and it is a very famous chelating agent, ethylene diamine tetraacetate. So one, two, this one, three, four, five, and six. So it will be hexadentate chelating ligand, right? So here is the explanation. EDT is a versatile chelating agent. it can form four or six bonds with a metal ion, and it forms a chelate with both transition metal and main group ions. It is a hexadentate ligand in coordination chemistry as it combines with a central metal atom with six bonds. Okay, and the second one is related to the theories, basically, which theory is given by the Hitler-Lundell model of the covalent bond. So you have already studied in the class the valence bond theory is given by Hitler-Lundell model, right? Okay, I think till here all the explanations are clear to you, right? So moving to the next two, what is the difference between a covalent bond and a coordinated covalent bond? Okay, so here are four options. So here are four options. Okay, first is covalent bond is the bond in which only ligands share the electrons. And coordinated covalent bond is only metals share the electrons. And similarly, B options is says covalent bond is the bond in which the metal shares the electron, or coordinated covalent bond is both metal and ligand share electrons. Okay, so similarly, three options are given, and fourth one is all of these statements are right. And the next one, which one is not considered in VBT theory, valence bond theory? So basically, you have to choose which postulate of valence bond theory is uh, which statement is not considered in the valence bond theory. Field orbitals of metal overlap with an empty orbital of ligands. Second one, it proposes that the geometry of the complex depends on the hybridization of metal ions. And third one, the chemical bond is formed by the atomic orbitals of the participating atoms. And last one, the filled orbitals of ligand overlap with an empty orbital of metals. Okay, so I am waiting for your answers. Thereafter, I'll explain. This session is a bit quicker because there is some network issue in my area. Okay, so moving to the explanations. A covalent bond is created by the mutual sharing of electrons. Okay, so both atoms in the bond share one electron, right? Whereas a coordinate covalent bond is a dative bond or coordinated bond formed by sharing electrons by only one atom. And covalent bonds are established between two atoms that are similar, either similar or different. Okay, so in coordination complexes, you just notice the coordinate covalent bond because ligand can easily donate their electron pairs to the central metal atom. Okay, and in covalent bond, if there is single bond, double bond or triple bond, there is a sharing of electron from both the atoms, right? So if they are sharing one electron each, right? So similarly, you can identify the single bond, double bond or triple bond will form, right? But here only ligand is participating in electron donation, so that will be called a coordinated covalent bond, right? So valence bond theory consider that overlap occurs between the atomic orbitals of the participating atoms to form the chemical bond. Here, the filled orbital of the ligand overlap, right? So metal is basically in any oxidation state. That means the metal is already electron deficient. So what that mean? Sorry, metal is already electron deficient. Okay, because it is having some oxidation state. So if it is having any vacant orbital, ligand which is already having a lone pair, that can easily donate its lone pair. Okay, so the effective overlapping will be there. So that is basically the postulate of valence bond theory. And this theory gives us about the basic idea about the geometry by the hybridization. Okay, so if you are having sp3, you will be getting the geometry of complex a tetrahedral. And similarly, if you are getting a inner hybridization, inner orbital hybridization, that is dsp2, okay, that will be a square planar type of complex. Okay, so what will be the right answer? Filled orbitals of ligand overlap with an empty orbital of metals. Okay, right. So in covalent bond, both metal and ligand share electron mutually, and coordinated covalent bond, only one atom share the electrons. Clear? So here you have to basically this complex. You are given this complex NiCN4 minus 2. So you have to define the geometry of this complex. Okay. So first calculate the oxidation number. What it will be? It will be X, because cyanide is minus 1, minus 2. That will be plus 2. So nickel will be in plus 2 oxidation state here. Right? Getting my point? So just write the electronic configuration for nickel plus 2. It will be 3d8. Right? So if I fill these electrons, 1, 3, 4, 5, 6, 7, and 8. Okay, but here it is a strong ligand. So these two electrons will be pair up. Right? So this orbital is vacant. It is basically 3d. Right? It is 4s. It is 4p. Because 4 ligands is here. Okay, so one d orbital is vacant, and there are 4 ligands, 4 cyanide molecules, right? 4 cyanide ions. So one pair due to this ligand will be here, one is here, and one is here. So what will be the hybridization? It will be dsp2, because the inner orbital is involving in the hybridization. So what will be the shape of DSP2? It will be square planar, right? So in this complex, the metal ion presents in a plus 2 oxidation state. The electronic configuration is D8. As the cyanide ligand is a strong field ligand, the hybridization will be DsP2 by taking one orbital of 3d, 4s and 2sp. So the geometry will be square planar, right? And the next one, uh, in the presence of an octahedral field, no splitting occurs for. In the theory class, you have already studied that s and p orbitals are not splitted in an octahedral field, but only d orbitals are splitted into a doublet and a triplet state, right? If they are okay, so these are 3D orbitals, right? So in an octahedral field, they are splitted. It will be a triplet degenerate configuration. It will be a doubly degenerate configuration. So same things is written here. In the influence of an octahedral field, d orbitals split into T2g and Eg orbitals. P orbitals are triplet degenerate. Okay, basically T means for triplet and A is a singly degenerate. Okay, so in the point group OH, the p orbitals are triply degenerate and do not split in energy and remains in these levels, right? Apart from that, s orbitals become present in a1z, that is basically a singly degenerate orbital. Okay, and the f orbital do split to t1z, t2z and a2z energy levels. Okay, so basically if you count basically add, triplet is 3 plus 3 and it is singly, that will be 7 orbitals, and you know the f orbital has 7 suborbitals in their configuration, right? So similarly add here 3 plus 2, that will be 5. Okay, so the next two problems, which one of the given complex is paramagnetic, right? You have to just select the complex which has, in which the metal ions have unpaired electron. If I talk about the dimagnetic complex, there will be no unpaired electrons, or electrons will be paired up. Just write their electronic configuration and get the information, right? Just try at your own. Here, the oxidation state of Fe will be plus 2. Here, the oxidation state of copper, that will also plus 2. And here, uh, also plus 2. And here is also plus 2. So all the metals are having a plus 2 oxidation state. So just write the electronic configuration for Fe plus 2, Fe plus 2, Cu plus 2, Ni plus 2, and Ni plus 2 similar. Okay. So here will be 3d6, right? And here it will be 3d cobalt, nickel, 3d8, right? And what will be here? 3D 9, right? So because in option A and B there is strong ligand, right? So what it will be 5. Okay, one, 2, 3, 4, 5, 6, and similarly in this one, in this one 4, 6, and 8, right? Okay, and similarly for D, what it will be? It will be, because chloride is a weak ligand, so the electrons will not be pair up. So one, 2, 3, 4, 5, 6, 7, and 8. So there are unpaired electrons, right? And in 3D 9, this one, it will be 1, 2, 3, 4, 5, 6, 7, 8, and 9. So one unpaired electron is there. So B and D both will be paramagnetic in nature, right? Getting my point? Okay. So the next one is, which one is correct statement for CFT? It is a purely covalent model for transition metal complex. It cannot predict the splitting of d orbitals. Ligands are considered as a point charge, and it cannot explain the color of transition metal complexes. Okay. So, right. So CFT is a bonding model of the purely ionic nature of transition metal complexes. In this model, ligands are considered as the point charge. Okay, so it predicts the splitting of d orbitals. It also explains many important properties of transition metal complexes, including their colors, magnetism, and structure. Okay, so this is also an incorrect statement. Ligands are considered as point charge. It is right. It is also incorrect. Okay, and this one is also incorrect because CFT is based on the uh, ionic model, right? Because ligands are point charge, they can electrostatically interacted with the central metal atom, right? So moving to the next two, what is the geometry of this complex cobalt tetrachloride, and how many unpaired electrons are present in the complex structure? Okay, so just determine the hybridization and unpaired electrons. Okay, just try at your own. I will wait for 2 minutes and thereafter I'll explain. Next one is the among the these are four complexes. You have to select which one is sp3 hybridized and dimagnetic in nature. So first determine the oxidation state. What it will be? It will be CO plus 2. Okay. So that will be 3D7 electronic configuration, and just put these electrons in the orbitals 6 and 7. Okay. So the unpaired electrons are 3. Okay. See. Right. So unpaired electrons are 3. And if I define the hybridization, so I'm having this configuration. This is 3D, 4S, and 4P. Okay. So here these electrons are already occupying the d orbitals, but these s and these 3p orbitals are vacant. So chloride ligand can give their electron pair here, right? So what will be the hybridization? It will be sp3, and geometry will be tetrahedron. So this option will be the right one. Similarly, you can calculate for the next one, amongst the complex, which one is sp3 hybridized and diamagnetic in nature. So first you have to choose, uh, you have to draw the electronic configuration, and you will be getting the idea about its magnetic property. If you are having the electron to be paired up, so the complex will show the diamagnetic nature. And if you are having any unpaired electron, you will be getting the paramagnetic complex. Okay. So just solve for these four and tell me the answer. Similarly, just I have solved the previous problems, you can solve this one also. Okay. So here is also the metal having plus 2 oxidation state. Similarly here, and similarly here. Okay. So you have to basically write up the electronic configuration for zinc in plus 2 oxidation state, nickel, cobalt, and again nickel. But the difference here and here is, because here is a cyanide ligand that can basically pair up the electrons, but here chloride is a weak ligand. Okay. So it will not pair up the electrons. So as I have already indicated in the last slides, that is, it is dsp2 hybridized. Okay. So it will be square planar, and it is not sp3 hybridized. Okay. And if I talk about this one, that will be having 3d7, right? Okay. So 3d7 is written here. Okay. So two unpaired electrons are there, so it will be paramagnetic. And for nickel plus 2, that is 3d8, the configuration will be 3, 4, 5, 6, 7, and 8. So two unpaired electrons are there. Okay. But here in this case you will be having a 3d10 electronic configuration. So all the electrons will occupy the respective subcell, and the remaining s and 3p, the hybridization will be sp3. So the last complex is sp3 hybridized and dimagnetic. Okay. Just simply the three basic steps. First, calculate the oxidation state, write down the electronic configuration, identify the ligand, whether it will be pairing up the electrons or not, and just calculate the number of electrons. And from there, you can easily determine what will be the hybridization, what will be the magnetic property, it will be diamagnetic or paramagnetic. Okay, and from the number of electrons, you can easily calculate the magnetic moment also. Okay, so from this practice, you can get many informations. Okay, so moving to the next two, you have to identify the soft acids. Okay, so what are the soft acids? There, the electron cloud can be easily polarized, right? They have low oxidation state and they are usually larger in size. Okay, so just identify from one example. In theory classes, you have understood that some complexes that is formed by the platinum with this ligand, that is thiocyanate. Okay, so basically platinum is found to make a bond with sulfur, not nitrogen. So it just basically indicating that sulfur is also a soft base, and platinum, it can be concluded that platinum is also in plus 2 oxidation state, it is a soft acid. Okay, apart from that, this chromium plus 3, cobalt plus 3, they are hard acids. Okay, they also are hard acids, right? In iodine, iodine is having a very large size. Okay, but these two are hard. So this first option will be the right one, because in this option, the this silver ion is having a plus 1 oxidation state, very low oxidation state. Apart from that, it is having a 4D configuration, right? So it is bigger in size. Platinum plus 2 is already a soft acid, and this mercury compound is also a soft acid, right? So these two questions are basically based on the HSAB principle, hard soft acid base principle. Okay, first you have to identify which is hard acid or hard base, and this principle states that hard acid will only form the bond with the hard base and soft with the soft, right? So just you have to identify the property which is not a property of hard acid or hard base, right? High oxidation state, yeah, hard acid is having high oxidation state, high electronegativity, right? Large ionic radius, low polarizability, right? So which one will note the property of hard acid? Basically, the soft acid or soft base, they are having a large ionic radius, but hard acid and hard base are having small ionic radius, they are smaller in size, right? So this will not be a property of hard acid or hard base. Understood? The next two, which of the following statement is correct? This is also related to the HSAB principle. Okay, so homo means highest occupied molecular orbital, and LUMO is lowest unoccupied molecular orbitals. Okay, so soft bases. What do you mean by soft bases? They can easily donate their electron pairs. The ligands, you can consider the soft Lewis bases. Rest depend on the metal or and its electronegativity, because nitrogen can easily donate its lone pair, but oxygen cannot, right? So HOMO of soft bases are of higher energy than hard bases, right? This statement will be correct. Why? Because the soft bases are having a high energy HOMO, right? That's why they want to be stable. They can easily donate their lone pair to the central metal atom and can be the energy of the overall system can be low. So that's why they are having a higher energy than hard base. But if I talk about the case of hard bases, their HOMO is already in lower in energy, so they will not easily donate the lone pairs, right? So the right option will be the first one. Second one, which of the following species is not paramagnetic in nature? Okay, so the complex is looking like this, and it is right. Okay, because sulfate is -2. It is the outer coordination sphere ion that is basically giving us the idea what is the charge on the complex ion. Okay, so follow the similar steps. First, determine the oxidation state, then identify the ligands, and you will be getting the answer. Okay, so here Az plus Mn is -3 plus 6, that is plus 3, and here also plus 3, and here what will be the oxidation state of copper? That will be plus 2 plus 1, 3, because this one is neutral. So just write down the electronic configurations, okay, and you have to identify the dimagnetic species. So what will be the electronic configuration of Ag plus? That will be 4010, right? So if I fill the electron, all the electrons will be pair up, whether it is a strong ligand or weak ligand. Okay. So there is no need to solve the other complexes. From here, you can just tell this species is diamagnetic in nature. Okay. The next two, among the following, the complex ion that is expected to show the highest magnetic moment at room temperature. So basically, the magnetic moment is directly proportional to the number of unpaired electrons, right? So more the number of unpaired electrons you will be getting, more will be the magnetic moment, because the magnetic moment formula is n into n plus 2 Bohr magnetron, right? So it is directly proportional to the number of unpaired electrons. So just write down the electronic configurations for all the complexes, calculate, count the number of unpaired electrons, and that particular complex ion that will having higher number of unpaired electrons will show the highest magnetic moment at room temperature, right? Because at room temperature is mentioned here because in future you will be studying about temperature independent paramagnetism. Okay, right? The next one is there are two complexes similar to other questions. You have to identify the magnetic properties. Which one will be paramagnetic? Which one will be diamagnetic? Okay, so you don't need to take care of this one, antiferromagnetic. This term will be discussed when you will read the magnetic properties of the complexes. Okay, this is basically related to the arrangement of the spin of electrons. So here this term doesn't matter. You have to just take care of these two. Which one will be the diamagnetic and which will be paramagnetic in nature. Both are having 3d8 configuration, right? So in the first one, these 8 electrons will be paired up. That means this complex will be diamagnetic. And in the second one, it will not be paired up. So that will be the paramagnetic complex. Okay. Are you getting my point? So these were the questions related to assignment 5, and I discussed these questions very fast. Okay. So if you are having any question, just put into the discussion forum. Okay. And I will be getting back to you. Right. So thank you very much for attending. I am just closing the session now. Okay. Yeah.